There's a stretch of coastline in Washington where the water turns to glass at dawn and nothing moves but the fog. No jolt, no warning tremor, none of that constant chatter you get from the San Andreas down in California. Just silence. And that silence? It's the most dangerous sound in North America. Because on January 26th, 1700, around 9 at night Pacific time, this exact fault let go. All of it. 600 or 700 miles of rock ruptured in one violent heave, dropping whole coastlines by several feet in seconds and shoving a wall of ocean west across the Pacific. Nobody in the Americas wrote it down. No European settlers were there to see it, but the water crossed 9,000 miles of open sea and slammed into Japan the very next day, tearing through fishing villages that had no clue where the wave came from. The Japanese named it the Orphan Tsunami, a wave with no parent earthquake anyone could point to. That was 326 years ago, and the fault hasn't moved since. So here's the first thing I need you to sit with, because it's going to matter enormously in a few minutes. For all that time, scientists have mostly pictured the Cascadia Subduction Zone as one long, continuous surface, one giant fault, one sheet of rock sliding under another, from Cape Mendocino in Northern California all the way up to Vancouver Island in British Columbia. Simple, uniform, a single loaded spring. That picture just got torn up. A team of marine geophysicists went out over the deep water off the Pacific Northwest, dragged instruments across the ocean for weeks, and came back with images of the fault nobody had ever seen. And what they found wasn't one clean surface at all. They found breaks, bends, places where the geometry of the descending plate changes so sharply the whole megathrust splits into pieces. 4 of them. 4 geometrically distinct segments, each behaving on its own terms. Which brings me to the second thing I need you to hold on to. Because when you carve a fault into segments, the obvious assumption is that it's good news. Segments can stop a rupture. A break in the geometry can act like a wall. A tearing earthquake slams into it and dies. Smaller pieces, smaller quakes, right? Wrong. And why it's wrong is the whole point of this story. One of those 4 segments, the one sitting directly off the Washington coast, is different from the others in a way that made the researchers uneasy. It's not the jagged, chaotic monster you'd expect to be the worst. It's the opposite. It's smooth, flatter, cleaner, and it reaches further inland than any of the others. That combination, according to the people who found it, points the danger straight at the 2 cities you'd least want it aimed at. Seattle, Tacoma, hold that. We'll come back to exactly why smooth is scary and what it means for 4 million people. But I want you to feel the weight of where we're starting first. The Cascadia Subduction Zone is a convergent boundary, which is the geologist's way of saying 2 slabs of the planet are colliding in slow motion. The oceanic Juan de Fuca plate, along with its smaller siblings, the Explorer and the Gorda, is grinding eastward and diving down beneath the North American plate, 600 to 700 miles long, running parallel to the coast, mostly underwater, mostly out of sight. And unlike a lot of the world's dangerous faults, it barely makes a peep. That's the part that fools people. Californians live with the San Andreas rattling constantly, hundreds of small quakes a year, a nervous system that never quite settles down. Cascadia does almost none of that. Very few small interplate earthquakes, long stretches of pure quiet. And to a lot of scientists, that quiet reads the way silence reads before something terrible. Not as safety, as a fault that is locked, stuck, refusing to slip a little at a time, and instead loading up strain year after year, decade after decade, until the whole thing releases at once. 326 years of loading, that's the number that haunts this. Now, I want to be careful here, because you'll hear people throw around the word overdue like Cascadia is a library book. It's not that simple. The recurrence intervals along this margin vary. In the northern stretch, full margin ruptures seem to run something like every 500 years on average. Down in the southern portion, near the Gorda Plate in Northern California, the ground tends to break more often, maybe every 200 or 300 years. So at 326 years since 1700, we're not past some hard deadline. We're inside the window of concern, comfortably, uncomfortably inside it. And here's what nobody could answer for decades. When Cascadia finally goes again, does it go all at once, the entire fault, a full magnitude 9 catastrophe? Or does it break in pieces, one section at a time, spread out over an agonizing run of years? Those are wildly different futures. One is a single day that reshapes the West Coast. The other is a slow-motion nightmare with no clear end. You can't answer that question if you're still imagining the fault as one smooth, continuous sheet. You have to know its shape. Its bends, its bumps, the places where the rock changes character, and that shape lives in the worst possible spot to study, buried under the seafloor, hidden beneath layers of ocean sediment offshore, in the exact zone where the biggest, most destructive ruptures actually begin. For a long time, scientists knew the deep part of the fault reasonably well, the section running under the land, where instruments can sit right on top of it. But the offshore portion, the piece that matters most, the piece that triggers the tsunami, that was a near blank. Sparse data, old surveys, educated guesses stitched over a stretch of crust that could kill more Americans than almost any natural event we can name. So a research vessel set out over that blank spot to fix it. To take, in effect, a giant ultrasound of the planet's crust. And what came back off that ship didn't just fill in the gaps. It rewrote the map. It split one fault into 4. And it forced everyone who studies this coast to look at that smooth Washington segment and ask a question they didn't want to ask out loud. To understand how they cracked it open, you've got to get on the boat. The boat is the R/V Marcus G. Langseth, and it doesn't look like a machine that rewrites geology. Gray hull, utilitarian, A-working vessel, owned by the National Science Foundation, run out of Columbia University's Lamont-Doherty Earth Observatory. In 2021, it steamed out over the Cascadia margin for a survey scientists now call CASI-21, the Cascadia Seismic Imaging Experiment. And its job was strange. It was going to make the seafloor talk. Here's how you image something buried under water and mud and rock. You don't dig. You can't. The megathrust sits kilometers below the ocean floor, hidden under sediment washed off the continent for millions of years. So instead of digging, you listen for echoes. The Langseth drags a long cable behind it, a streamer packed with hydrophones, sensitive microphones, tuned to catch sound moving through the earth. Reports from the Washington Post's coverage of the survey describe a streamer on the order of 9 miles long, studded with something like 1,200 hydrophones, though the exact configuration is worth checking against the expedition's own records. The ship fires a pulse of acoustic energy straight down through the water. That energy punches into the crust, bounces off every boundary where the rock changes, every fault, every layer, every hidden seam, and comes racing back up. The hydrophones catch the returning echoes, and a computer turns thousands of them into a cross-section. A slice through the earth. A picture of something no human eye will ever see. Sit with what that means. You're floating on the surface of the Pacific, and you're drawing an accurate portrait of a fault 12 miles below you, one that hasn't slipped since the evening of January 26, 1700. That's the ambition. Not a guess. Not a model built on old, thin data. An actual image. The person driving that ambition was Suzanne Carbotte. She's a marine geophysicist at Lamont-Doherty, the Bruce C. Heason Lamont Research Professor, to give the full title, and she led the imaging effort. Carbotte had spent a career reading the language of these seismic reflections, and she understood the stakes better than almost anyone. The onshore part of the Cascadia megathrust had been studied for decades, but the offshore part, the dangerous part, the part where the great ruptures actually begin, that was the blank she'd come to fill. In press coverage, she said it plainly. For years, scientists had solid information about the deep landward portion of the fault, and almost nothing about the offshore stretch where the destructive quakes start, precisely because it's hidden beneath the seafloor. Working alongside her was Harold Tobin, a professor at the University of Washington and director of the Pacific Northwest Seismic Network, the regional system that watches this coast for every tremor. Tobin's the one usually asked what all this means for the people who actually live in the shaking zone. Madeline Lucas, a University of Washington researcher, worked on mapping the fault geometry. Brian Boston, a marine geophysicist, dug into the structural analysis. This wasn't one lone genius. It was a crew, a ship, and a haul of data big enough to argue with. And here's where I have to stop you, because you probably already have a picture in your head of what a fault looks like. Most of us do. We imagine a single crack, one clean line where two plates grind past each other, a seam running up the coast like a zipper, all of it built the same, all of it behaving the same way. That's the mental model. And that's roughly how Cascadia had been treated too. One continuous surface, a uniform slab of Juan de Fuca plate sliding under North America from Cape Mendocino, California, all the way to Vancouver Island in British Columbia. 700 miles of the same thing. That picture is wrong. That's the twist buried in the Cascadia 21 data. And it's why this study landed so hard when it published in Science Advances in 2024. When Carbotte's team assembled their cross-sections and looked along the length of the margin, the fault didn't behave like one object. The subducting plate, the Juan de Fuca slab bending down beneath the continent, changed. Its geometry shifted. Its angle changed. Structures crossed the margin, cutting the fault into pieces. And when the team traced those changes, the megathrust broke into at least 4 geometrically distinct segments. 4, not one uniform surface. 4 different faults, effectively, stacked end to end along the coast, each with its own shape, its own depth, its own personality. Carbotte, describing it afterward, said there was far more complexity in the megathrust than anyone had previously inferred, that it wasn't one continuous structure, but divided into at least 4 segments. Read that and let it land. For decades, hazard maps, tsunami models, evacuation plans, a lot of it rested on the assumption of a fault that was more or less all one thing. And a ship dragging a 9-mile microphone across the Pacific quietly took that assumption apart. So why does breaking one fault into 4 matter this much? Because segments have edges. And edges do things. In some earthquakes, a segment boundary acts like a wall. The rupture races along the fault, slams into that boundary, and stops. That would mean a smaller quake. Good news, maybe, but there's a colder reading, and it's the one that keeps these scientists up at night. Segmentation also means the fault has more than one way to fail. It could rupture in pieces. It could rupture as a chain. And if one of those 4 pieces happens to be big, smooth, and locked over a wide area, that single segment could produce a monster on its own. No help needed from its neighbors. Now hold on to that, because it's the hinge everything turns on. 4 segments aren't 4 equals. They don't share the danger evenly. One of them is different. One is flatter and smoother than the others, and it reaches further inland than the rest, closer to where people actually live, closer to the cities, the harbors, the freeways, the schools. The old picture of a uniform coast had accidentally hidden that. Averaging 4 different faults into one had smeared out the very feature that should have been screaming for attention. And that's the thing about taking a real image instead of trusting a model. The Langseth didn't invent this segmentation. It didn't add complexity to make headlines. It simply recorded what was already there, 12 miles down, waiting. A structure that had been shaping how this coast would break for longer than humans have kept records. The data came back. The map changed. And every set of eyes on that new map drifted, almost against its will, toward the same stretch of the Washington margin. Toward the one segment that behaved like nothing they expected. Toward the one aimed at 3.5 million people who have no idea it's there. Look at the Washington segment on the new map and it almost disappoints you. There's no jagged menace, no wild kinks in the plate, no chaotic tearing. The subducting slab under Washington runs flat, smooth, astonishingly even, compared to the crumpled geometry the team found further south off Oregon and Northern California. Your instinct says smoother means safer. A cleaner surface, less friction, less drama. That instinct is exactly backwards. And it's the part of this study that made seismologists go quiet in a bad way. Here's why. A rough, warped fault tends to snag. It catches on its own irregularities. Rupture starts, hits a bend or a bump in the plate, and stalls. The energy dies before it can spread. That's a mercy built into ugly geometry. But a flat, smooth contact between 2 plates has nothing to stop it. Once it slips, it can keep slipping, kilometer after kilometer, because there's no barrier to catch. The Washington segment is the widest, cleanest, most uninterrupted stretch of the four. If it's locked, and the evidence points that way, it's locked over a huge continuous area. That's not a small fault. That's a launch pad. And it does something the other three don't. It reaches further inland. The locked zone, the part welded shut, quietly storing strain year after year, extends further landward under Washington than under Oregon or California. Sit with what that means geographically. The energy of a subduction quake radiates hardest from where the fault actually slips. Push that slip zone east, toward the coastline, toward the mainland. And you push the worst shaking closer to where people actually live, closer to the water, closer to the Puget Sound lowland, closer to Seattle, closer to Tacoma. Harold Tobin, who directs the Pacific Northwest Seismic Network out of the University of Washington, framed the human stakes bluntly. For places like Seattle and Tacoma, he said, it could be the difference between a scary jolt and a total disaster. Read that twice. He's not talking about whether the ground shakes. It will. He's talking about whether it shakes for 30 terrifying seconds that rattle windows, or whether it shakes long and violent enough to collapse the things holding a modern city up. Same fault. Same region. The difference lives in the geometry the Langseth finally photographed. Now stack this on top of the number we started with. 326 years. That's the gap between right now and January 26, 1700, the last time this margin let go in a great earthquake, an event reconstructed to roughly magnitude 8.7 to 9. 2. From Japanese orphan tsunami records and the drowned ghost forests along the Washington and Oregon coast. A full margin rupture is generally put in that same range, magnitude 9.0 or higher. And the study's authors raise the unsettling possibility that the big smooth Washington segment might not need the whole fault to cooperate. It could rupture as a major event on its own. That's an interpretation, not a settled forecast. The paper opens the scenario, it doesn't guarantee it. But the fact that it's now on the table at all is new. Before Cassie 21, the Washington margin was just part of one long line on a map. Now it's a distinct, mapped, worryingly capable piece of machinery. I want to be careful here, because the loud version of this story gets a lot wrong. Overdue is the word everyone reaches for, and it oversimplifies. Recurrence along Cascadia varies by where you stand, commonly cited as something like 500 years for full margin ruptures in the north, and more frequent, roughly 200 to 300 year cycles down in the southern Gorda and California portion. At 326 years, the northern margin isn't past some hard deadline. It's inside the window of concern. That's a real distinction, and it matters, because the danger here was never a countdown clock ticking to zero. The danger is a smooth, wide, locked surface with no natural break, storing strain under one of the fastest growing regions in the country. There's a cruel irony threaded through all of this. Cascadia is quiet, almost eerily so. It doesn't chatter with small earthquakes the way the San Andreas does. That silence used to read as calm. Now it reads as a warning, a fault so thoroughly locked that it isn't releasing pressure in little installments. It's holding. All of it. And the smoother the Washington segment turned out to be, the more that silence starts to sound like a held breath. This isn't sitting in a journal collecting dust either. The findings from Suzanne Carbotte's team at Lamont-Doherty and their University of Washington collaborators are exactly the kind of offshore geometry that hazard scientists have been starving for. The National Science Foundation, which funded both the Langseth expedition and Crescent. The Cascadia Region Earthquake Science Center, launched in 2023, is precisely the pipeline through which better fault images become better community fault models, and eventually better maps of who's in danger and how building codes should respond. Carbotte put the core discovery plainly. The megathrust is not one continuous structure, but divided into at least 4 segments. There's a whole lot more complexity here, she said, than was previously inferred. Complexity that had been invisible because the destructive part of this fault hides beneath the seafloor, exactly where the big ruptures begin, exactly where we had almost no detailed information until a research ship dragged a listening cable across it in 2021. So go back to that coastline. The one from the beginning, The tide going out over gray sand, gulls working the rack line, a couple walking a dog past driftwood at a state park south of the strait. Nothing about it looks loaded. Nothing about it ever has. That's the whole problem. For 3 centuries, this margin has performed stillness while 12 miles down. A flat sheet of Juan de Fuca crust has been jammed against the underside of North America, refusing to slip, hoarding strain, and pointing. We can finally say pointing, because now there's a picture. Toward the harbors and hospitals and highway overpasses of 3.5 million people who built a modern civilization on top of it without knowing its shape. The fault didn't change. It was always 4 pieces. It always had a smooth, dangerous stretch reaching towards Seattle. The only thing that changed is that we finally looked, and looked hard enough to see it. That's the strange gift and the sick weight of this study at once. Cascadia is no longer a rumor under the water. It has an outline now. And the worst part of that outline is aimed at the one place we'd least like it to be. The coast stays quiet.